Hello everyone, welcome to another class of fundamentals of electrical circuits. So for today's video, we're going to talk about the second topic under AC analysis, which is phasors. Now let's define first what is phasor. A phasor is a complex number that represents the amplitude and phase of a sinusoid. It provides a simple means of analyzing linear circuits excited by sinusoidal sources. Solutions of such circuits would be intractable otherwise. The notion of solving AC circuits using phasors was first introduced by Charles Steinmetz in 1893. So before we completely define phasors and apply them to circuit analysis, we need to be thoroughly familiar with complex numbers. Now let's define some terms related to phasor. First, a scalar number is the type of mathematical object that people are used to using in everyday life. A one-dimensional quantity like temperature, length, weight are examples of a scalar quantity. A complex number is a mathematical quantity representing two dimensions of magnitude and direction. And lastly, a vector is a graphical representation of a complex number. It looks like an arrow with a starting point, a tip, a definite length, and a definite direction. Complex numbers are numbers of the form a plus bi, where I squared is equal to negative 1. I is an imaginary number. And a phasor is a complex number that represents the amplitude and phase of a sinusoid. Now let's have some operation involving phasors. We add and multiply complex numbers in the obvious way. So if we have here add 2 plus 3i and 5 minus 6i, of course we will add the real number to another real number. Then this will be 2 plus 5 equal to 7, and the imaginary number to the imaginary number, so 3i plus negative 6i, then we will have negative 3i. So our answer would be 7 minus 3i. Another problem, multiply 2 plus 3i and 5 minus 6i. So we'll use FOIL method here. So first, 2 times 5, so that is 10. Outer, that is 2 times negative 6i, that is negative 12i. Inner, 3i times 5, that is positive 15i. And last, 3i times 6i, that is negative 18i squared. But remember that I squared is equal to negative 1. So this will be equal to negative 1. So simplifying, we'll have 10, negative 12i plus 15i is equal to 3i positive. The negative 18 times negative 1, that is positive 18. So 10 plus 18, that will be 28. Then plus 3i. So this is our final answer. Now sample problems. Another set of examples. Compute each of the following. So for letter A, we have 58 minus I plus 2 minus 17i. Okay, so we'll add 58 plus 2, that is 60. Negative I minus 17i, that's negative 18i. For letter B, okay, so we'll apply FOIL method. Let's write the solution here. So we have 6 times 10. So first, 6 times 10 is 60. Then outer, 6 times 8i, that is 48i. Then 3i times 10, that is 30i. And last, we have 3i times 8i, which is equal to 24i squared. So this will be 60 plus 78i plus 24 times negative 1, that is 60 plus 78i I minus 24, and that's equal to 36 plus 78i. Now for letter C, again, let's use FOIL method first. So this will be 16. Outer, 4 times negative 2i, that is negative 8i. Inner, 2i times 4, that is 8i. And last, we have 2i times negative 2i is negative 4i squared. So we'll have 16, then negative 8i plus 8i, that is 0. Then we'll have negative 4 times negative 1. We have 16 plus 4, or that's equal to 20. Or you can just use the property for the sum and difference of two binomials, since we have 4 plus 2i and 4 minus 2i. So this will be 16 minus 4i squared automatically. But since we use the long method, so we just prove that the answer is just the same, whatever method you use. And our final answer would be 20. So in AC circuit analysis, we have to remember three important forms. First one is the rectangular form. Z is equal to x plus jy, where x is the real number and jy is for the imaginary number. So in AC analysis, this format will be familiar to you in our next topics because Z will be denoted by impedance and our X is the resistance. Our jy will be the reactances, so it can be inductive or capacitive. Then polar form, Z is equal to R angle of phi, where R is equal to the square root of x squared plus y squared, and phi is the phase angle. Okay, so this is our phase angle. Then for exponential form, we have z is equal to r e raised to j phi. So our polar form and exponential form is almost the same. So our r is equal, then our phi is also the same. So just the form is different and also the name. So polar, exponential. So z is equal to x plus jy is equal to r angle to phi, then is equal to r cosine phi plus j sine phi. So to convert from polar, so this is polar, right? Polar form. If we will try to convert the polar form into rectangular form, so all you have to do is to use this format. So r cosine phi, that is equal to x, then j sine phi is equal to the jy. Okay, and then I will show you how to use your scientific calculator to just convert the rectangular to polar form. Now to convert rectangular to polar and vice versa, let's use the complex mode of our calculator. That's complex mode 2. And let's have an example 2 plus 3i in rectangular, and we wish to convert it into polar form. Use shift number 2 and 3, that is r angle theta, and equal. So we will have square root of 13 angle of 56.31i. Then if we will convert polar into rectangular, example, we have 3 angle of 60, and just type it and equal, then you'll have 1.5 plus 2.598 and so on and so forth I. So that's how you convert rectangular to polar and vice versa.